morning, everybody. I think you can hear me well. Well, I would like to thank my colleagues who nominated me, to thank the French Chemical Society for giving me the award, for inviting me here. And I have to tell you that it gives me immense pleasure to be here, because I looked back, and it was almost exactly 2 years ago that I attended my last live conference, face-to-face conference, and that was right here in Auvergne, in Saint-Nectaire. So, well, it's good to be back. It's good to be back in more than one sense. Okay, what I'm going to talk about is less about achievements, more about prospects. And I will talk about things that may seem a little bit exotic to the chemical audience. But on the other hand, listening to really fantastic lectures that were given yesterday and today, I found that there are a lot of concepts that actually overlap. So I'll be talking about things that have been mentioned in other contexts in several of the talks. But first, let's start from this. Yes, I looked at publications of mine for the last couple of years, and these are the places where our collaborators come from in France. Of course, we collaborate not only with France, but we have, I think, the biggest number of collaborations with this beautiful country. However, for me, it wasn't always so. It was that, as mentioned by Fred, my CV is quite complicated. Let's see. Okay, I actually graduated from my institution in Wroclaw, Poland, but then, well, things were complicated for me, and I spent indeed 18 years in Australia. I spent quite a few years in other countries. But what was really the most important for me was my postdoctoral stay at the National Research Council in Ottawa, where I started working with lasers. And I haven't stopped since. Okay, because lasers are great. And when the first laser was produced in 1960, well, they thought it's just a solution looking for a problem. They did not foresee a multitude of applications that are possible having lasers around. So, for example, there are some applications that have been patented, like, you know, a method of exercising your cat with a laser. Okay, we're not really looking at this sort of applications, but yes, there are some applications which are quite unique for lasers. Why they are great? Of course, they give coherent beams, they give narrow spectra of emitted light, and what's important for me is you can generate short pulses of light. And if you generate short pulses of light, you can get high light intensities, which lead to nonlinear optics. And actually, it's 60 years of nonlinear optics right now, because the very first paper on nonlinear optics was published in 1961 in July. And as you can see here, well, there was second harmonic generation, and there should be a dot here showing the spectral evidence of the second harmonic generation. But you don't see it. Why? Because the editor thought it's just a tiny little faint spot. He thought it's just a speck of dust. Okay, because the effect was extremely inefficient. So who cares about such inefficient processes, inefficient effects? Well, in fact, this 10 to minus 8 photon conversion efficiency, these days we can get 50% conversion efficiency in a device that costs less than 10 euros in a green laser pointer. So how come? Do we have better materials? Yes, we do. But there are also other tricks that are necessary to really make use of nonlinear optics. Like in this case, so-called phase matching. The material that Franken used, quartz, doesn't allow for phase matching. So we have to be smart when looking at new materials for nonlinear optics, and that's what I'm doing. Because there's more than one effect that we have to look at. Okay, so what are these applications of nonlinear optics? Some of them are very well known, like frequency mixing, like Potter's effect, like nonlinear refractive index, like nonlinear absorption. The last application that I mentioned here is the most important for us. It appears it's the most flexible application that can be used in many, many domains, in many areas. What are the standard nonlinear optical materials? Something that was really worked out over the last 60 years, like crystals, inorganic crystals, like beta-barium borate, like lithium niobate, like glasses, silica glass, chalcogenide glasses, semiconductors. But for the application that I mentioned for nonlinear absorption, of course, the standard materials are dyes, organic or organometallic dyes. So we want to go beyond that. And if we go beyond that, what are the chances that our work will lead to something practical? And this is like a little bit optimistic, a little bit pessimistic view that I have of these materials. In some areas, I don't see much chances. In some areas, yes, for nonlinear absorption, indeed, these new materials that we're working on should be useful. And another thing is that because we're chemists, I'm not a physicist, I'm a chemist, although sometimes I pretend I know a little bit of physics. But what's important is that being chemists, we know how much we can modify our materials, and we can achieve, among others, multifunctionality. And this multifunctionality may be used in many different areas, and the most interesting ones are that have bio as a prefix. Nonlinear biophotonics, things like theranostics. And I will mention that not only we are looking at multifunctionality, but also at ways of improving the nonlinear optical properties of our new materials. And I mentioned some change of paradigm that I'm introducing for several years now, nonlinear optical pigments. Okay, this is the title of the grant that I just finished a couple of weeks ago. Nonlinear optical effects and their physical-chemical consequences. Because if we have interaction of laser beams, one or more laser beams in a material, we can have many different effects that are taking place, not only just the nonlinear optical interaction, but things like generation of heat, generation of some photoreaction products, photochemistry, generation of charge carriers, which leads to photoconductivity. We could have magnetic effects that are driven by nonlinear optical processes. We can have structural changes, order creation, and so on. All of this may be potentially useful. So how do you get these multifunctional nonlinear optical materials? Well, you need to have these basic NLO functions, but you also need to have some functions which are built into your materials. And some of these could be structural changes, electrical effects, magnetic effects, and other interesting functionalities. What are the sources of such multifunctionality? Well, you can have just a material that is multifunctional per se. But also you can make mixture, you can make blends, you can create hybrid structures, hybrid nanostructures. You can engineer these nanostructures to a large degree, for example, by using nanocontainers containing some cargo. And there was a talk about that yesterday. I will mention that too. There could be some ordered structures, which are sometimes called metamaterials, which are very interesting. So what materials are we looking at? My group is looking at lots and lots of different classes of materials, like organometallics, yes, we've been doing that for a long time. Like nanoparticles of various kinds, plasmonic nanoparticles. There was an excellent talk about it yesterday, about plasmonic. We're looking at gold nanorods and other things. We're looking at quantum dots. We're looking at quantum rods. We're looking at lanthanide-doped nanocrystals. We're looking at hybrid structures containing elements of those. We're looking at nanocontainers that I mentioned. We're looking at 2D systems like graphene, like other low-dimensional systems. We're looking at biopolymers like DNA, like amyloids, I will mention them. We are looking at coordination polymers, including a subclass of coordination polymers, metal-dynamic frameworks. We are looking at metamaterials. Quite a lot of things to do. Okay, but this multifunctionality, actually, I published my very first paper in nonlinear optics, which was published 40 years ago, was about photoconductivity generated by nonlinear optical absorption. So, well, these things have been around for a long time, but perhaps not really have they been completely exploited. In this case, what we showed was that you could have interest in photoconductivity in the range where the material is completely transparent at low intensities. At higher intensities, it starts absorbing. Okay, so the mechanism there was two-photon absorption followed by photoionization of excitons. And this mechanism can be quite complicated. Magnetic effects, I will not talk about them, but we want to study magnetic effects that are driven by nonlinear optical absorption. And there could be many different effects. I'll just mention in here paramagneticity that is present in some excited states. I'm mentioning here spin crossover transitions, which again were the subject of a talk yesterday. Light-induced changes in magnetization, ferromagneticity, which can be generated by light. This is all a very, very fruitful, potentially, area. Okay, we started looking at some exotic materials, exotic for nonlinear optics, but also exotic for other applications. But not exotic for people who are looking at magnetic effects or electrochromic effects or other effects. Prussian blue is a fantastic coordination polymer that has all of these properties. What we found was that it's also an extremely strong nonlinear absorber. There's nonlinear absorption in this material in the range of around 1300 to 1500 nanometers that has the spectral shape of two-photon absorption, but actually we find that it also has signatures of three-photon absorption. So what is going on? Well, we proved first that this is a very strong effect compared to other sort of record strong three-photon absorbers, which are like polymers, like dendrimers, like semiconductors. But what we're finding is that the effect is actually quite complicated. It involves the presence of some intermediate state, which has the lifetime of around 260 femtoseconds. What sort of a state is that? We don't know yet. But we know that this sort of materials can be very, very interesting from the point of view of multifunctionality. We have the first step. That is, we know that they can show extremely strong multiphoton absorption effects. Okay, but what are these other interesting functionalities? Biological. We're looking at detection or manipulation of nucleic acids using nonlinear optics. We're looking at biosensing using nonlinear optics. Nonlinear microscopy, which is a very well-known area where nonlinear optics is useful. We're looking at light-activated therapies. So, light-activated therapies, just of course, in this audience, I don't have to explain what photodynamic therapy is. It's generating reactive oxygen species using some sort of a photosensitizer and light. And then this reactive oxygen species can be used to kill cancer cells, but they can also be used to kill bacteria or some other bad guys. So what are the limitations of photodynamic therapy? The problem is that the photosensitizers, the best photosensitizers actually work in the region of the visible. And in the visible, the transmittance of tissues is not really very good, and there are some side effects that are possible. It would be good to shift this photodynamic therapy into the infrared. How does one do that? Well, we could use two-photon absorption, of course, because that shifts our operating wavelength into the infrared. But most of the photosensitizers that are used now have relatively weak two-photon absorption, so they are not really very good for this application. So what we proposed was a certain paradigm in which we want to use multiple photons, so we use upconversion processes for generating excited states, but we split the roles of multiple photon absorber and the photosensitizer, which is the species generating reactive oxygen species. And then what we need is energy transfer between these two participating entities, and to maximize that, we encapsulate. Again, there was a talk about encapsulation yesterday, so you see that there are many concepts that really are universal. Okay, talking about upconversion could be of different mechanisms, and of course harmonic generation is a kind of upconversion. Two-photon excited or multi-photon excited luminescence is a type of upconversion, but there are also other upconversion mechanisms that are not strictly nonlinear optics, because they do not involve high values of electrical field, but rather some series of processes, some sequential processes, like in upconversion using lanthanides, again a subject that was covered yesterday, or triplet upconversion. So in our approach, we combine this upconversion with energy transfer. We try to encapsulate. The nanocontainer should be of the proper size. Around 100 nanometers is about perfect because of the so-called EPR effect. And we functionalize the nanocarrier, which is again easy, to provide targeting functions. And as the result, we have this theranostics, and theranostics is a portmanteau of therapeutic and diagnostic. Why diagnostic? Because we want our device, we want our capsule to be, let's say, loud about its presence, to luminous, so we can detect it and we can monitor what is going on during the therapy. So this is an example. Nanocapsules containing quantum dots, cadmium selenide, core shell quantum dots, and the photosensitizer, which is a zinc phthalocyanine in this case. We encapsulate them, and then what we find is that really such a capsule has a brightness which is 1,000 times bigger than the brightness of a single quantum dot. Could we get that using a bigger quantum dot? Of course not. Because a bigger quantum dot would not be a quantum dot. But if you have 1,000 of them inside the nanocontainer, it's a very, very bright species. Very, very easy to detect using nonlinear microscopy. And, well, we have this energy transfer. We can prove that using certain spectroscopic techniques. And what we have, this is one of the examples that by measuring the lifetime of the luminescence, we can prove that there's energy transfer going on. And the efficiency of this energy transfer was not extremely high, around 20%, but it's a beginning. And we can also prove that indeed, reactive oxygen species are being generated. One way, simple way of doing that is by using a probe like this one, which is oxidized by singlet oxygen, and then its absorbance decreases, so we can follow this change of absorbance to calculate how much singlet oxygen we are generating here. So yes, this sort of an approach works. But the problem is that in this nonlinear optics-driven photodynamic therapy, you do need a laser. And femtosecond lasers are still a bit expensive. There are already femtosecond lasers that are this big, like, not a shoebox anymore, it's closer to a matchbox these days, but they are still expensive. So can we somehow change that? Yes, we can. We can use another way of upconversion to generate excited states that will, in the end, generate our reactive oxygen species. So for upconversion using lanthanides, we could just use for excitation just an ordinary light-emitting diode, not a laser anymore, just a light-emitting diode, only it needs to have the right wavelength to excite our lanthanides. Okay, so yes, we do need to be careful how we excite these lanthanides. We need to have a scenario of exciting them, but once we do that, yes, it will be a capsule, a species that will be very, very bright, and that will give us this upconversion here. We excite it using 980 nanometers, and it glows red, because it contains, among others, europium ions, which are very well known as red emitters. And this is, these are examples of the spectra. I will not really go through that, but these are typical spectra of emission of lanthanide ions. And in this case, we encapsulated verteporfin, which is another photosensitizer, together with this lanthanide-containing nanoparticles, and we looked for energy transfer and looked for reactive oxygen species generation. Indeed, it works. It doesn't work perfectly yet, but at least we demonstrate here that it is possible to combine these things, to combine upconversion using lanthanides with energy transfer and with generation of reactive oxygen species. And by the way, that was fabricated in a green chemistry approach. Okay, so maybe I will not talk about these pictures. These are just microscopic pictures showing these very, very bright species that are theranostic nanocapsules. Okay, so conclusions, yes, we can generate reactive oxygen species through certain scenarios that avoid the need for a special photosensitizer. We just divide the roles of photosensitizing and absorption. And in addition, these nanocapsules are very bright markers, so they can easily be detected. Okay, now the other thing is, once we have certain scenarios in which we need nonlinear optical materials, we want the nonlinear optical materials that have possibly the highest values of the nonlinear optical parameters. So how to enhance the nonlinearity of the known materials? We look at quantum size effects, we look at aggregation effects, we look at plasmonic enhancements, we look at synergetic effects in hybrid systems, but, well, there's a limit. Mark Kusic published a series of papers in which he theoretically assessed how far we can go. There is a theoretical limit to the nonlinearity. Don't believe it if you read in the paper that somebody went orders of magnitude above that. No, that's probably wrong. But, as comes from this series of papers of Mark, we're still not at the limit. We can still improve the properties of our materials. So, aggregation effects. Aggregation effects can exist in many different systems. Dendrimers, micellars, J-aggregates, amyloids. Amyloids are very, very special proteins that are examples of very strong aggregation. And we found several years ago that compared to native proteins, they have orders and orders of magnitude stronger nonlinear optical properties. They are actually relatively strong nonlinear absorbers. They show 2-photon absorption, 3-photon, even up to 5-photon absorption under suitable light intensities. And this can be used, for example, for imaging amyloids in the presence of other forms of proteins. This is a paper that we haven't published yet, but in this paper we show that amyloids show 2-photon induced luminescence, that is at around 500 nanometers. And we can excite it at around 750 nanometers. It's a relatively strong two-photon absorption. So this sort of effects can be used for imaging amyloids. That can be even used for assessing orientation of things which are on sub-nanoscale, using polarization analysis of the two-photon excited luminescence that comes from these amyloid structures. So there are biological applications of the aggregation, but could we use aggregation to improve the properties of some dyes that we already have? And we focus on so-called aggregation-induced emission dyes, dyes which work completely opposite to the common dyes. Common dyes, if they aggregate, they lose the possibility to emit light. On the other hand, some dyes, as they aggregate, they actually gain this tendency to emit light. So what we did in one of the papers was we proved that such dyes, these AIE dyes, not only increase the emission quantum yield, but they also increase the two-photon absorption cross-section. And there are good reasons for that. It's rigidification of the structure, it's interactions between the planes of the dyes, it's all explained quantum chemically. So yes, aggregation can lead to quite sizable enhancements of nonlinearity. But how do we control this aggregation? Well, one day my PhD student came to me and said, well, why don't we look at coordination polymers, especially at metal organic frameworks? Because metal organic frameworks are really aggregated systems and aggregated in an orderly manner. So we could use ligands which are already chromophores, which are already two-photon active chromophores, and we want to have certain enhancement of their properties. And indeed, we first surveyed the literature. This is a review that I highly recommend for people who want to know about whether metal organic frameworks can be useful nonlinear optical materials. And there are some issues. First of all, these coordination polymers, metal organic frameworks, are powders. They do not dissolve in anything. So can you use powders for nonlinear optics? I will show you that we can. And I will introduce this concept of NLO pigments. Because normally what we have as nonlinear optical materials are glasses, crystals, liquids, nano objects. But what if we just have powders? Well, we have to go and make this sort of devices out of the powder. Of course, sometimes we do crush our material to obtain the powder, because the powders are useful in certain types of measurements, or nonlinear optical measurements, like powder second harmonic generation. But this powder generation doesn't really have any real-world application. Even laser target cards that are sold, they do not really use second harmonic generation. They use upconversion using lanthanides. So yes, we still do powder measurements just to have some information about the presence or absence of center of symmetry in some materials. We have to be careful there, because in materials like metal organic frameworks, you usually have lots and lots of different transitions, different excited states. So one has to find areas in the spectrum where this generation of these harmonics is not hampered by the presence of absorption. So this is an example where we have a series of 3 MOFs containing Cl, Br, and I. And in one range of spectra, you see this iodine containing is the weakest, and another region, it is the strongest. So one has to be very, very careful when analyzing and interpreting powder measurements in nonlinear optics. Still, we're doing that. We're doing that, for example, for detecting ferroelectric transitions in which we lose the center of symmetry. We also use these powder measurements to detect third harmonic generation, which is again some sort of assessment of the suitability of a material for nonlinear optics. This is an example of such a measurement. Again, the spectral dependence of third harmonic generation is mostly controlled here by the presence of absorption. But what about these nonlinear optical pigments? Pigments are insoluble, but pigments are still useful for staining some materials and can be useful in themselves, like for example components of inks. We could make inks that contain pigments. Okay, we published another review very, very recently in which we talk about the concept of nonlinear optical pigments. We talk about coordination polymers, about perovskites, about 2D materials. We talk about the nonlinear optical absorption properties that could be wavelength dependent, types of mechanisms that could be present, how this nonlinear absorption can be used in practice. And one example of nonlinear optical pigments that we've also been looking at are cross-linked conjugated polymers. We tried to use them as remote thermometers. They do not work very well yet, I can tell you that. But some other materials like MOFs actually work quite well, because metal-organic frameworks, some of them, actually have very, very good fluorescent properties, very high fluorescent quantum yields. That's an example. That's one of the first papers on nonlinear optical absorption and nonlinear optical absorption excited luminescence in MOFs. And in this case, it was possible to excite this material by 2-photon absorption, 3-photon absorption, 4-photon absorption, and in all cases, this efficiency of the excitation was high, was much higher than in the case of the ligand itself. So we did have this enhancement due to the aggregation of the ligands inside the metal-organic framework. Okay, how do we determine the values of the parameters which characterize these things? Because we need to have that. We need to compare molecules with crystals, with powders. So yes, we actually discussed several of these techniques. There's one of the techniques that we use, the internal standard technique, in which we compare the components of the spectra coming from the MOF with the component of the spectrum coming from the luminescent dye, and then we can calculate the cross sections of the involved species. And this is an example of work in which we used a certain ligand, which is already a good 2-photon absorbing molecule. And these are 3 different MOFs containing 3 different ions. And as you can see here, there's not really much of a difference in the cross sections for these 3 MOFs. And moreover, there's not much difference between the spectrum of these MOFs and the spectrum of the ligand itself. So no, we don't really have much of the enhancement in this case. Even worse, there is an example where we made a very nice MOF containing interesting ligands, which should be AIE ligands, and unfortunately, the MOF has a lower value of the cross-section than the ligand itself. But if you contract the MOF, and it contracts by itself when heating, actually the cross-section increases again. So no, that wasn't a good attempt, but it just shows that things are complicated. We do not really understand all the mechanisms that lead to this aggregation-induced enhancement. Okay, the end. Not yet. Okay, the real-world application. Again, yesterday there was a talk about remote thermometry using luminescence. We use that, but we add nonlinear optics to it. So this is a metal-organic framework that was synthesized in our lab, and it contains several different lanthanide ions. This pair, terbium and europium, is a very typical pair for remote thermometry. And indeed, the spectra that we see here In this case, we are close to room temperature because we are interested in the biological range of temperatures. So close to 37 degrees, right? A little bit more, a little bit less. And indeed, in this range from 0 to 100, these are not Kelvins, these are Celsius, centigrade, okay? So this is the biological range. And you can see that the changes of spectra are really very, very distinct. And these changes can be followed in two ways. Either exciting by one photon absorption in the UV, as most people do, or exciting by 800 nanometer laser. And again, in this case, we find that it's not two photon absorption, it's three photon absorption. But that doesn't matter. We still have very, very good spectra, and we still have the dependence of the spectrum, or so-called thermometric parameter, on temperature. This is a little bit different between the one photon case and the three photon case. These calibration curves are a little bit different, but there are good fundamental reasons for that. The mechanism is as follows. We have ligands, which are organic, which are, let's say, nonlinear optics active. We can excite them with one photon in the UV or three photons in the near infrared. Then there's energy transfer, so they act as antennas. There's energy transfer to the lanthanides, and then there's energy transfer between the lanthanides. And in the end, we have this several luminescence bands that we can follow. And as you can see, the result is really very well visible. This is just powder. We can process it in any way we want. We could make it nano size, we could make it micron size, but that's just powder. And as you can see here, the changes of color are really very, very well visible. So, and also we can follow the lifetime, which is another indicator of the temperature, which is independent. So we can have ratiometric measurement of temperature, or we can lifetime measurement of temperature. And yes, what's the advantage of using nonlinear optics? There are several. First of all, we use the wavelength that is benign, other than the UV, which of course in the biological context is not really a good thing to use. Then we can have penetration of our laser beam much better into the tissue if we want to measure the temperature of the tissue, for example, doing some sort of light activated therapy. We could map in 3 dimensions. We could, what else? I think I covered more or less the advantages. So again, this is a demonstration of several things. First of all, that it's good to combine different concepts coming from different areas. Second, that metal-organic frameworks, or in general, coordination polymers or hybrid system or inorganic systems, they are a very, very fertile field for a nonlinear optician like myself, but also for people who are looking for applications in bio-related areas, maybe not only in bio-related areas. We could make an ink out of this material and use it for some other purposes, like detecting the temperature of some mechanical parts which are inaccessible. Okay, in any case, it's time to finish the conclusions. Yes, metal-organic frameworks are very, very interesting. We only started looking at them. We could have applications which are based not only on the nonlinear optics itself, but also on some combinations of effects, on multifunctionality. And we always, my group at least, is focused on things that are in the form of numbers. We are not happy if we just see an effect. We want to quantify it. We want to compare things, which ones are better, which ones are not better. So we are very careful about the characterization techniques that we use for our nonlinear optical materials. And acknowledgements. The agencies that funded me in Poland: National Science Center, and Foundation for Polish Science. And the most important, my dream team, the team that I formed when I came back to Poland in 2008 and started working at my alma mater again. So this is an old picture of my dream team, and this dream team is growing. My younger colleagues are forming their own groups now, and getting the money for doing the research. And we have lots and lots of collaborators. I just named two of collaborators here because I took some results from the work that was done together with them. And as I mentioned, yes, my alma mater, Politechnika Wrocławska, Wrocław University of Science and Technology, was really good to me when I came back as prodigal son 13 years ago. And yes, they helped to acquire a new laser system, which just has been commissioned in spring this year, and we're getting lots and lots of new good results. And thank you for your attention and staying up to the end of this ceremony. Thank you.